Let's say we have a degree n polynomial, call it m of x. And some polynomial p of x. Then we have the following theorem. P of x is congruent to some polynomial r of x modulo m of x, where r of x is of degree at most n minus 1. And we can see this by doing polynomial long division. P of x can be expressed as some quotient, q of x, times the divisor, m of x, plus some remainder term, r of x, where r of x is of degree n minus 1. Now let's apply this theorem to the above problem. Let m of x equal x squared plus 1. Now using the above theorem, we know that any polynomial modulo m of x is congruent to some polynomial of degree at most 1. So how many polynomials of degree at most 1 are there? Well, we have 0, 1, 2, x plus 0, x plus 1, x plus 2, 2x plus 0, 2x plus 1, and 2x plus 2. So in total, there are 9 possible remainders. Suppose we have two degree 1 polynomials whose product is divisible by x squared plus 1. Let the first degree 1 polynomial be ax plus b, and the second one be cx plus d. And if their product is divisible by x squared plus 1, then it must equal k times x squared plus 1. Now let's examine the roots of the two sides. The left-hand side has a root at b times a inverse, and a root at d times c inverse. Now these two numbers are not necessarily distinct, but we have that there exists at least one root. Notice how a inverse and c inverse always exist since they're never equal to 0. However, on the right-hand side, if we evaluate x squared plus 1 at 0, 1, and 2, we get 1, 2, and 2. Now, any non-zero constant times x squared plus 1 will never equal 0. Thus, we have a contradiction, and we have that no two non-zero degree 1 polynomials can have a product that's divisible by x squared plus 1. Euclid's algorithm is the following procedure for computing the GCD of two numbers. If b is equal to 0, then the GCD is simply a. Otherwise, we return the GCD of b and a mod b. Now let's try and generalize this procedure for computing the GCD of polynomials. If we have two polynomials, p of x and q of x, where the degree of p is greater than or equal to the degree of q, then we can borrow some intuition from that of the original Euclidean algorithm. The GCD of p of x, q of x is equal to the GCD of p of x minus q of x and q of x. Now if we repeat this procedure repeatedly, we get the GCD of p of x mod q of x and q of x, where p of x mod q of x is of degree at most the degree of q. So flipping these, we get this. And now we simply repeat the procedure over again. So the only difference between the algorithm for computing the GCD of two polynomials and the GCD of two integers is that instead of testing if the number is equal to 0, we test if the degree of q is equal to 0. Then we return p. Otherwise, we return the GCD of q of x and p of x mod q of x. This mod here represents the remainder after doing polynomial long division between p and q. Generalizing the extended Euclidean algorithm follows the exact same pattern. We replace b equals 0 with degree q is equal to 0, and we replace mod with the remainder of polynomial long division. The procedure for computing multiplicative inverses for polynomials modulo x squared plus 1 is identical to that of computing multiplicative inverses for integers in a finite field. If we have some polynomial p of x, its inverse, p inverse of x, is such that their product is congruent to 1, modulo x squared plus 1. This means that p times p inverse plus some polynomial k of x times x squared plus 1 is equal to 1. Now, if p of x and x squared plus 1 don't share any common factors, then we may apply the extended Euclidean algorithm that we developed in the previous part to compute the two polynomials p inverse and k. Thus, p inverse of x is found by EGCD. Now, we noted in part 10 that no degree 1 polynomial is a factor of x squared plus 1. Thus, any degree 1 polynomial is coprime to x squared plus 1. In that sense, GCD of some degree 1 polynomial p and x squared plus 1 is equal to 1. Thus, there always exists a multiplicative inverse of p. So there exists a p inverse. If we have two degree 1 polynomials, p and q, we may add them in the natural way. We can also subtract them. So p minus q is defined as p plus negative q. We can also multiply them modulo x squared plus 1. And as we showed here, there exists a p inverse, so we can also divide them. So p divided by q is defined by p times q inverse modulo x squared plus 1.